Hi guys, welcome back to another virtual recitation. Today we're going to be looking at calculating volumes using integrals. And the first problem we're going to look at is section 5.2, number 66. So this problem asks you to find the common volume to two cylinders, each with radius r, if the axes of the cylinders intersect at right angles. You are going to take the following four steps every time you're trying to calculate a volume using the disk method and using integrals. So the first thing that you're going to do is you're going to draw a picture. Drawing a picture for this is very challenging. I actually ended up having to look up a picture online, which is totally okay when you're looking at regions that are really difficult to draw. And so the picture I came up with, I tried to draw here, but this is not perfect and better images exist. I'm going to link a picture in the description box to the video, so hopefully you guys can check that out and get a little bit of a better idea of what this region looks like. And so I drew a picture and then I looked at it and I was like, okay, this picture has some symmetry. If I look in each octant, which is how you break up three-dimensional space into different planes, it's sort of like the different quadrants in the two-dimensional case. In three dimensions, we have octants. But the picture in each octant is one of these tented regions with a square base, and it's sort of got these like sloping up sides on all four sides. And there are 8 of these, one in each of these octants. And so what I decided to do is I decided to calculate the volume of the entire thing by calculating the volume of one of these tenths and then multiplying that by 8. So I'm actually going to calculate the volume of one of these tenths. To figure out the volume for one of the tenths, I start by looking at the cross-sectional area. So the cross-sectional area is the area that would happen if I took the tenth and I sliced it with a plane for a value of z, for a value of the height. So if I slice it, I end up with one of these red squares here. And so I want to figure out a formula for the area of one of those squares. So to figure out a formula for the area of one of those squares, first of all, I'm going to let the variable a be the side length. So the area of a square is the square of a side length. So the area is equal to a squared. But what I really want is for the area to be written in terms of x, y, z, and r. So I want to figure out how I can write this area in terms of x, y, or z, and my radius r. And the way that I do that is by actually writing down some equations that define the cylinders themselves. So if I look at this cylinder that's popping out of the board here, the cylinder that's popping out of the board is a circle with radius r that is in terms of x and z that is then run up and down the y-axis. So the popping out cylinder is defined by the following equations. It's defined by x squared plus z squared equals r squared, and y is any number. So I want to use this relationship here to write a squared in terms of r and one of my other variables. So this point here is actually on one of the cylinders. And this point here corresponds to the point x, or a, any value of y, and then z. So there's a relationship between x and z given here, and my x there is actually just a. So I have a squared plus z squared equals r squared. And this allows me to solve for a squared. A squared equals r squared minus z squared. So that is going to be my formula for the cross-sectional area. The third thing that I want to do is I want to determine my integration boundaries. So my area is now written in terms of the radius and in terms of z. So I need to think about the values of z that define my tent. So when I think about the tent is resting on the xy plane, which means that at the bottom of the tent, the value for z is 0. At the top of the tent, I am on the z-axis, and x and y are both 0, which means that I have to be at exactly the radius above the origin. And so up here, z is equal to r. You can also think about, if z was bigger than r, you would no longer be on the cylinder or inside of the cylinder, right? So that would be another way to reason out why z equals r is the top boundary of your integration. So now the last thing we want to do is we want to integrate. So the volume is equal to 8 times the volume of my tented region. So I integrate over these boundaries, 0 to r, and I'm integrating the cross-sectional area, which is a function of z. And I'm going to integrate with respect to z. So this gives me 8, the integral from 0 to r, of r squared minus z squared dz. I'm integrating this with respect to z. So the integral, or the antiderivative of r squared, because r is constant with respect to z, that's going to be r squared times z. It's just like if you took the integral of 3 with respect to x, you would get 3 times x. When you take an integral of a constant, you end up with that constant times your variable of integration. So this is going to be 8 times r squared z minus the integral of z squared with respect to z is z cubed over 3. Now, I'm evaluating this at z equals r, z equals 0, and then subtracting. So I'm plugging in r for z. This gives me 8 times r squared times r cubed minus r cubed over 3. And then if I plug a 0 in for z here and here, I get 0 both times. And so that evaluates to 0. So I have 8 times r cubed minus r cubed over 3. 1 minus a third is 2 thirds, so this is 2 thirds r cubed. 8 times 2 thirds gives me 16 thirds. So this is 16 r cubed over 3. And that's my final answer. So just a quick recap of the steps you're going to take to solve this problem. First thing that we did is we drew a picture. Again, totally okay to look up challenging pictures online. The second thing that we did is we found the cross-sectional area. After I drew the picture, I decided that it was easier to use the symmetry of the problem to break it into 8 identically volumed regions. And I looked at each of these tents and I calculated the cross-sectional area of the square using a relationship that's determined by the cylinder. So I wrote down these equations which define the cylinder, and that helped me build a formula for the cross-sectional area. The third thing that I did is I determined my integration boundaries. In this case, z equals 0 corresponds to where the xy plane cuts the 10. Z equals r corresponds to this point all the way up on the z-axis where x and y are both 0. Again, if x is 0, what does z have to be to satisfy this equation? R. Okay, so then the last thing that I do is I actually integrate with respect to z. Really important. When you have when you have multiple variables in your problem, you really need to think about what variable you're integrating over. Very common mistake is integrating this with respect to r, okay? But you're actually going to integrate with respect to z here. And so I perform my antiderivative, I subtract, and I get my final answer of 16/3. All right, so that's all for this problem, but stay tuned for the next one. Thank you. Bye.